Alright, today we want to look at the average value of a function, and this concept is connected to the mean value theorem for differentiation that we studied earlier, which said that if you have a continuous differentiable function, if you do the average rate of change between two endpoints, a and b, represented by the secant slope and by this equation, then there must be at least one point in between where the tangent slope is the same as the secant slope. So on my picture here, right here, here's one particular point where this slope is equal to that slope. So this slope here is represented by f prime of c. And this was the mean value theorem. Now with our more recent study of integration, I could take this statement and I could rewrite it as f prime of c equals 1 over b minus a. And then the f of b minus f of a is the definite integral from a to b of f prime of x dx. So this statement is the same as this statement here. And in fact, this is the basis for the definition of the average value of a function. So here it is. The average value of a function, sometimes called the mean value theorem for integration, says that the average value is defined as this statement. All I've done here is, instead of talking about f prime, I've just talked about a general function f. Now, as with anything, once we have a new concept, we want to be able to understand it better, visualize it in some way. So let's take a look at what we've got happening here. This right here is the net signed area between a and b of f of x. So I've just drawn a graph here. Represented in this part represents the block area down below. Now what I'm doing here is I'm taking that area and I'm dividing by b minus a, which is this distance here. So then if I take the area of something and divide by a quantity, which I can think of as width, what I will get is an outcome that can be represented as the height of a rectangle. So what I want to do is I want to think of a rectangle that has the same area as this black region, and its width along the bottom is b minus a, and its height is f of c. So this area in red is equivalent to the area in black. Let me see if I can move my rectangle over. I can, if I fit it right in there. So the height of the rectangle is the average value. So you can think of taking your average value statement and multiplying both sides by b minus a to get this. This is the length times width of one rectangle whose area would equal the area under the curve, represented by the definite integral. So there's one way to interpret, understand what average value means. I have a couple of applets that you can look at that'll give you some other interpretations and other points of view that are useful. There's another one that says you can think of average value as if you took every single y value on the interval and averaged them, the average value you get is what we're talking about here, f of c. So check out the applets I've got below here. They'll give you a more in-depth and well-rounded point of view of how to think about average value, and I'll also post these on Schoology. Now the next question that you might be thinking about is there a connection between the average value of a function, which I've just defined, and the average rate of change, which is something we talked about earlier in the course? Are they the same thing? Are they related? Well, let's take a look at this. So again, let's start with something we know. We know that the average rate of change of a function is represented by its secant slope, what I've got outlined here in red. And this statement here, through the first fundamental theorem, is connected to this statement over here. And so if we were to put this into words, we could say that the average value of f prime, which is what this expression represents, is equal to the average rate of change of its antiderivative f on that interval. So visually, on my f graph, this expression is the secant slope, And what we're saying is that on the derivative graph, the average value is the height of the rectangle that averages out the area under f prime. Alright, let's look at some specific formulas. So this expression here, my definite integral going from t1 to t2, and I'm dividing by 1 over t2 minus t1. This expression represents the average value of velocity. The statement on the right is the average rate of change of position with respect to time. So the average value of velocity is the average rate of change of position with respect to time. And since rate of change of position with respect to time is velocity, average velocity is the same as the average value of velocity. So we now actually have two different ways to calculate average velocity, an integral way and a division way. The same thing applies with acceleration. This statement would represent the average value of acceleration. This statement would represent the average rate of change of velocity with respect to time. But by definition, the rate of change of velocity is acceleration. So average acceleration is the average value of acceleration. These two statements are equivalent. So to state all of this more generally one last time, the average value of any function f is equivalent to the average rate of change of its antiderivative, big F, over that interval.